Good afternoon. I'm Peter Denning, your host here for the Harnessing AI series. Welcome you back. Today we're going to be talking about an important topic in artificial intelligence, robotics. We have Professor Doug Horner here to talk with you about that. It's interesting that the term robot was, as he may tell you more about it than I will, was invented in 1902 by a playwright doing a play. So people have been thinking about the possibility of robots being intelligent for far longer than the field of AI has existed. There's a lot of things that robots, we wish they could do, but we still don't know how to make them do it. And Doug is going to talk to you about how difficult some of the design problems are in making robots work. So I'd like to introduce Professor Doug Horner. He's from our Mechanical Engineering Department. And he'll tell you a little bit about himself, but he's a real expert on robots. He's going to enlighten you with all sorts of things that you've never probably even thought about. So thank you, Doug.
Thank you. All right, quick introduction. My background. A long time ago, I was sitting where you guys are, take a course. My master's at the postgraduate schools in applied mathematics and defense analysis. I spent 12 years as a SEAL, came over here, started working for here, and then got my PhD in computer science. And I've been working in the mechanical engineering department for the last 20 years or so. So I know and really appreciate MPS, and this is actually my last week. This is going to be my last presentation. I'm retiring on Thursday. So this is kind of exciting for me too. Okay. Thanks. Total of 38 years, and it flies. It really flies. All right, I'm going to throw a lot at you, and I'm not going to apologize for it. And if you got questions at the end, let me know. Okay, so what I'm going to talk about is a particular event within robotics, and that's the influence of artificial intelligence within robotics. I can't believe it's 2021, when I last gave this presentation for HIA. I talked about this right here. And these are the components that are associated with when you think about higher level autonomy on board robots. So start over on the top right-hand side. The robot or the plant, and in this case, you've got a REMUS vehicle. How many people are familiar with the REMUS underwater vehicle? Well, I got a couple. I got some pros in the audience, and then down on the right-hand side is sensor processing and perception. That's represented by you get sensory information, but then you have to figure out what is it telling you. Okay, so you've got algorithms that are running up against that then allows you to try and interpret that information and make it useful. Use that for position estimation, fundamental thing that's associated with robotics. And what's the challenge? Well, when you don't have GPS, when you don't have an exterior beacon system that allows you for localization, like in the underwater domain, in space, and indoors, you've got to figure out where you are by other means. And it's a huge area within robotics that's sometimes associated with the term SLAM, simultaneous localization and mapping. The mapping portion of it is that in order to be able to navigate within an environment like right here, if you had a quad rotor, for example, is that you've got to have some kind of understanding as to what your ability to navigate is within the environment. So it's the building and representation of an internal representation of the environment, okay? And that could be stochastic or deterministic, depending on what your prior information is telling you. And then on the top left-hand side is path planning. So you take into consideration your sensors, you do position estimation, you're building a map of the environment, and now what are you going to do? You're going to move, you're going to act. And so this is all about the components that are associated with motion planning. And what's particularly challenging that's with robotics is that process that you're looking at right there has got to happen in near real time. So that's an important consideration from a computer science standpoint. What you think about is the time and space complexity associated with your algorithms. So that should never go far away when you're combining together the mechanical aspects of things with your algorithmic aspect of things. That's why I like it so much. That's why I got a PhD in computer science and work in the MAE department, because they complement each other very, very nicely. And it's two kind of different ways of thinking about things. All right, so before, what I tried to describe for you was an OODA loop, right? And that's the observe, orient, decide, and act that we're all familiar with as military officers. While sufficient, these descriptions hide the challenges that are associated with autonomy, reasoning about uncertainty over time in order to achieve long-term mission goals. The thing that has kind of fundamentally changed in the last 4 years is the generation or the rising of a term that's sometimes called embodied AI. And fundamentally what that means is that before in that OODA loop is that you had a series of pipelines that were connected to one another that I showed you just in the last slide. But now what they're thinking about from a machine learning standpoint is a multi-level fusion taking into consideration all those aspects of perception of languages and interpretations of commands, and also the ability to do the path planning. Okay? So this is a fundamental point of the talk for today, is that all the components are still there, but now they're all mashed together. And what does that mean? Well, that's an obfuscation of understanding the individual components, because now they're going to be all put together, and now you're going to have less fidelity about maybe what's happening within the process. Instead of pipeline, they're all jammed together, and your perception about what's happening within that machine is now, it's a lot more difficult to understand what that is. All right, so embodied AI requires learning algorithms to handle interaction, environmental uncertainty, and real-time decision making. Multimodal AI systems that are unified rather than pipelined. The components are the core components associated with machine learning that many of you are already familiar with. Reinforcement learning, deep learning, imitation learning, transfer learning, and sim-to-real transfer. So in this talk, the things that are highlighted in green are some of the aspects that I'm going to be touching upon. Fundamental point that I'd like to make at the beginning, I'll probably reinforce it at the end, is that data and the representation of the data as input is extremely important. As military officers, what do we see all the time? We see the collection of side-scan sonar, of LiDAR, of communications information that's happening within a carrier battle group, and that data goes away. Just imagine if we were set up 20, 30 years ago with the ability to save the data and represent that data so that we could utilize it in a way for designing these systems, how far we would be as a leader within the world with respect to DoD operations. All right, so I'm no subject matter expert on embodied AI. There's a lot of other people that are better accustomed to be able to talk about this. But in a nutshell, there's kind of two ways of thinking about it. One is a VLA model, which is vision, language, action models, which is represented there on the right-hand side. And that's relatively for a single task. So think about a vision system with a manipulator that's trying to disassemble a group of blocks and reassemble it. Another system that's coming to the forefront is end-to-end systems. So now, don't just think of that as a single task, but now what's the behavior that's associated with, what's the combination of behaviors that's associated with doing long-term healthcare, for example, or cleaning up a kitchen. So with the VLA models, joint processing of vision, language, and action. And so what does that mean? That means that you're taking an image, you're taking the language, you're taking the state that's associated with the vehicle, and you're tokenizing that. So you can see in the algorithm on the bottom right-hand side is that this is a very abstract algorithm, but you've got 400 vision tokens associated with a particular image. You've got 12 language tokens, you've got 64 dimensions in the state encoding, and then you are fusing that together to create its own tokenized state. And then as a result of that, you're training and then you're outputting what the action is going to be afterwards. Recognize again the complete difference in approach. Rather than having separate pipelined AI, machine learning, within that OODA loop, now they're all mashed together. And how it's so difficult to be able to, in the future, to understand what's actually happening in there. And so one of the things that I think about is how to make it more transparent. How to understand when you have these big vectors and you don't understand what the heck the input is, what is the physics of the situation? Okay? On the top right-hand side is an example from a really good summation paper that I've got listed down in the bottom right here, and it's multimodal input and the tokenization of the vision, language, state, bringing them together, and then the action tokenization to then have an action, a result, an execution. And that continues. So the notion of sense, plan, and act, which is very similar to the OODA loop, does not go away. But the way in which we're handling it is changing. All right, so what are the challenges that are associated with that? Real-time performance, accuracy, reliability, knowledge distillation, and transfer. Okay, so here's kind of 3 different areas, really 2, with a caveat on the point on the third topic right there. What I want to talk about is the projects that my students have been doing with respect to the first one, which is sim to real transfer, and that's learning model parameters in virtual environments. The second one, which is transfer learning, and this was a student last year that's a submariner that did something for self-assessment for terrain-aided navigation. So it's the idea of you let the vehicle go, how is it doing? How can it convey that information to the other folks that need to understand about the environment? And then the community within robotics is generally coming to a consensus on how to come about and establish reward functions for optimizing. And that's generally information metrics. And those information metrics, you have to understand how to quantify the information given the environment, giving the sensing or the map building, and what are the strengths and limitations of such an approach. All right, so for the first one, this is being done by Lieutenant Commander Andrew Fox, who's an EOD officer within, I should have mentioned before, I'm the chair for the Undersea Warfare Academic Group. So I've had a long history within submarines. I used to be an SDV driver, SEAL delivery vehicle driver, and I have an affinity for the underwater environment. So everything that you're going to see is associated with underwater robotics. And a partner in crime right here is Sean Craglin. For just about 20 years, the 2 of us have been doing this. All right, so learning model parameters in virtual environments. This Defender vehicle, the one in obviously yellow, is the Navy's EOD platform for mine clearance. And what happens is that you could have a manipulator on it, you could have a battery pack on it, you could have different sensing devices, and all of those are different configurations that can be put into deployment. And all of those then would have an impact on how that vehicle works within the environment. So one thing is that for human operators, which is the way they operate right now, is that you have a joystick, and if you could work in a virtual environment with the hydrodynamics that are associated with the vehicle in high fidelity, then they can get a sense on what the art of the possible is if you've got a strong current and you've got objects within an environment to get down to a potential mine-like object. Okay. So what are we going to do? Well, the goal is to develop stochastic estimates of the hydrodynamic model parameters. And the payoff, of course, is the combination of a virtual environment and a hydrodynamic model facilitates operator training, as I was saying before. What you can do is verify and validate high-level autonomy algorithms. You can verify data sets develop data sets for embodied AI. So we don't necessarily need real-world data sets, as there's advantages and disadvantages associated with collection of data sets within the virtual environment. And I'm going to show you an example of a virtual environment. And then use ML techniques with real-world data sets in the virtual environment to determine the hydro parameters of reconfigurable Defender. Okay, so that kind of feedback loop. What's the big point right here? Is that with the multi-level fusion that's happening and giving you less understanding within the model, is that we can develop parallel approaches that then allow you to say, well, this is what the recommendation of the ML algorithm was, and here's our physics-based approach, and how is it similar, how is it different? Can we make it approach the same way so that the vehicles are operating in the same way, and how is that impacting the hydrodynamic coefficients? So parallel physics understanding with this kind of unknown as to how an ML algorithm is doing its multi-objective optimization. All right, so the hydrodynamic model. I'm not going to spend a lot of time on this, but there's a couple things that I'd like to point out. Up on the top left-hand side, this is something known as the Fawcett model. And it's nothing more than the way it's written right there. Mass times acceleration is equal to force. Okay? And on the left-hand side, you've got added mass. You've got the centripetal and Coriolis. That's the C matrix. You have the damping, which is the drag that's associated with a particular platform. And then you have the restorative forces, which is associated with buoyancy and gravity. You add those up, and then on the right-hand side is a vector of forces relative to the body. So if I am the body, that's representing the defender vehicle, X is this direction, Y is this direction, Z is this direction, and then roll, pitch, and yaw is K, M, and N. Okay? So it outputs what those relative forces are. So breaking that down is that you have all these coefficients, 90 of them, that is associated with trying to understand what the motion of the vehicle is. You see some of them right there. Some of them are really easy. The mass of the vehicle is super easy. The center of mass is also fairly easy. But some of these terms like that X U dot is associated with a damping term of the matrix. That's not so easy to get your arms around. So that's M, D, C, and G over there. When you have a vehicle like the Defender, you've got 7 thrusters. You've got 3 thrusters that are vertical, 2 in the front, 1 in the back, so you can induce a pitch on the vehicle. And then you have 4 thrusters that are at angles like this that can then allow you to go forward, side slip, heave, and then rotation. But you can also actually get pitch really well on this vehicle and a little bit of roll. What you're doing is the wrench is the way of understanding how those 7 thrusters can impact the X, Y, Z, K, M, and N, the forces. Okay? So it's a 7 vector with the thrusters versus 6 on the forces. And there's different ways to establish what the X component is. You could use the 2 in the front, you could use the 2 in the back, or maybe you could even use 1 in the front, 1 in the back. So that's the secret in the sauce, right? What the vehicle manufacturers have to figure out. And for every vehicle, you've got something that's kind of similar like that. So, like I said before, about 90 unknown parameters within the hydro model. And what we want to do is understand the forces acting on the vehicle through the application of thrusters. So last week, 2 weeks ago actually, Videoray, the manufacturer of the vehicle, put their vehicle in a tank, had a weight down at the bottom, had the vehicle up here, and then had a tether that allowed us to understand the forces in the separate directions, which is really pretty cool, by the way, in this direction, this direction, this direction, and up, right? And that's what you're looking at the top right-hand side. Those are forces in newtons in X, Y, and Z. The red represents the X. As you look at it from left to right, you see the red, the positive right there, 75 newtons, is the forward thrust that vehicle can apply. Backwards, it's not quite as much because the props aren't designed for that, right? So it's around 55, 60. And notice that there is some thrust that is associated with different directions, even though you're applying thrust in only the X direction for those first 2 parts of that slide or that printout. So what are we doing now? Is that we can now have a little bit of an understanding as to what the minimum and maximum forces for each of the individual, in the body direction. So next week, we're taking the vehicle to John Hopkins APL, where there's a tank and there is a motion caption system because we don't have GPS. So you've got to be able, there's cameras that are located. If you look carefully around the perimeter, you can see some of them. So it then can quantify what the pose is, position and orientation. So now we're going to apply forces, and now we're going to then register what the impact of the forces are. Okay? So that's the way that we're going to train our model. We get these data sets, we know what the forces are, and now we can try and back out what, in the hydro models, your output is accelerations. You can integrate accelerations over time, and then you can get positions, so you can get an idea as to what the position is over time and see how your model works versus the real data, and train your model on the real data. I hope that makes sense. All right, so what we want to do right now is infer what those values are. Really all this is, to pull the veneer back, is a multi-objective optimization function. Each of these techniques. But they're high dimensionality. So on the top one, maximum likelihood estimation gives an initial point estimate without priors. Gives you a ballpark idea as to what the parameters are, given data sets. So the parameters, if you look at the last term on the top MLE, theta is the parameters, D is the data. Okay? So it's the data given the parameters. So all you're doing is kind of switching that parameter space, and you're saying, okay, I'm going to modify it a little bit, and I'm going to see how it fits the data set. Does it work? No, it doesn't really work. Here's the error term. I'm going to use that error term as a feedback loop. Okay? Next one down, maximum a posteriori, incorporates a physics-based prior knowledge to constrain and refine the point estimates. But no stochastics yet. The stochastics are associated with the last one, that's Hamiltonian Monte Carlo simulation, and what it does is use a Hamiltonian matrix within the configuration space and calculates a potential and then populates that and looks at what the errors are and tries to get better, tries to improve the estimate over time. Okay, so what's the methodology? Collect a data set in the virtual world with known parameters, and then use the described methods to learn the parameters. So I showed you before the tank, the motion capture, but we can also set up to see whether or not our hydro model is working within this sequence of techniques within machine learning. So what do? We set up the model and assume that we know what the model is. Then we run it within the virtual environment. And then we see what the delta is. And then we iterate using each of these techniques. Okay, if it produces good results, we can extend it to other vehicle configurations. So here's some results. Now the x of u dot is the damping force that's happening with a change of forward velocity with respect to the vehicle. The simulator value was set to 0. The learned value was 0.07. Likewise, the other ones did a really good job. The last one, B, is for buoyancy. Nearly nailed buoyancy. Gives us confidence that this methodology, this multi-objective optimization, is working. So what do? We got to build this virtual environment. So that's what I'm going to focus on right now. And this is all for those that are familiar with robotics within ROS2 nodes. So robotic operating system, and it facilitates a number of things that allows for programming robots in an effective way. It's kind of the industry standard. On your left-hand side is the virtual environment. In the middle is the controller. On the right-hand side is the hydrodynamic model. Why am I doing this from a macro level? Our goal is to replace the virtual environment with the real environment. Our goal with the hydrodynamic model is to have the vehicle operate in the real world in the same way that it works within the virtual world. This controller doesn't move. It stays the same. So you have a secondary controller architecture that you plug on to any vehicle, and you can learn the hydro parameters associated with the vehicle, and then you can validate the controller within the virtual environment. This is really powerful, right? And this is why, with respect to virtual environments, that so much money is going into, and these companies that focus on auto driving in simulated environment are worth so much money. It saves The government, it saves the companies, the government, DoD, tons of money. And it's my opinion that over the last 4 or 5 years, because of the increase in computation, that these models, where these virtual environments that have been developed by gamers, are really getting good. Okay? So let's take a look at it. The virtual environments. The one on the left-hand side is the one we're utilizing. It's known as HoloOceans. A guy by the name of Josh Mengelson and has developed it with his students, and it's based on the Unreal Engine. For those of you gamers, probably recognize that. Numerous undersea environments, surface and underwater vehicles, and a ROS 2 capability. And then on the right-hand side is what we've developed. Well, that's not true. This one was part of AEV Simulator, so we borrowed that, but we're using that. We've developed the virtual JHU test tank, and then we also have a representation of the video array based upon an STL file that came from SolidWorks. So now I'm going to jump out of this, and I'm just going to show you a demonstration. Okay, so what are you looking at right now? This is the virtual world. Okay, and these are the ROS processes that are around them within a Ubuntu system, and you're going to see position and you don't need to know all that. So this has all 3 of those components working. And there's something that I want to kind of point out here, which is additive and useful. And it's this right here. Oops. You see that QR code that's right there? Okay. So there's a camera that's on board the vehicle, and it's publishing this image, and there's processing that's happening on that simulated image that recognizes that. It's called an April tag, but it's the same thing as a QR code. And now it's giving you position and orientation associated with that camera. So remember I was talking about position estimation before in an underwater environment where you don't have GPS? This allows you to get that without any fancy techniques, but you got to have knowledge as to where that QR code is, where that April tag is on board that blowout preventer. Okay. Everybody tracking with me? Okay. Okay. I'd like to extend the discussion in one more project area, and this was done last year by Amanda, and it's called active terrain-aided navigation. People may be familiar with the notion of terrain-aided navigation, and it's where you have a prior map, and now you navigate relative to that map. Any submariners are here? Okay, submariners are familiar with this concept. What happens if you don't have the prior map? Can you still do terrain-aided navigation? And as long as you have information as to where you are doing the navigation, the answer is yes. But what it becomes is the ability to simultaneously build the map and navigate relative to it. So conceptually what this means is a classic problem within robotics, which is known as exploration versus exploitation. So as the vehicle's moving along, you don't know what the terrain looks like, but you're mapping it relative to a whatever start position that you want, normally 0, 0 up on the surface before you lower down. It's mapping some area, but also the positional uncertainty, you can think of it as a bubble. That bubble is increasing over time. Okay? So the positional uncertainty is increasing. So as the bubble gets bigger, what you want to be able to do is find a piece of terrain that you can localize based on. If you can do that, you've collapsed the bubble and you have positional certainty relative to your local map. When you have a bubble that's small, it allows you to explore. It allows that to expand. But there's going to be a point in time that you want to collapse that as well and get back to positional certainty so that you can create a map and return that map or do whatever the mission objective is. Okay, so it's an active component with dynamic path planning based upon the vehicle and the mission objective. So the format that we use is information theoretic approach based on stochastic estimates for the vehicle position and bathymetric mapping. And it's appropriate for undersea without beacons, covert missions, and undersea when surfacing is undesirable. So this is a good approach for navigating and staying underwater where you have changes within the bottom topology, or you've got some kind of way, you've got a chain that might be associated with red right returning on a buoy system, for example, if you're coming into a harbor area. Limitations, requires information in the terrain, and what's really fun about this, from my standpoint, is that when you let go of that vehicle, you don't know where it's going. It's going to make its own mind up. So we think of autonomy, but this is truly unique autonomy that as military leaders we're going to have to get our arms around. You can tell to somebody, I'm going to give you a box. You can just do whatever you want within that box. But that's not the way that we operate right now. You pre-program it, you send it out, you have an expectation as to where it is along the way. Using techniques like this, which are going to be part of the landscape that's associated with DoD robotics, is that you have to give that up. All right, so the dynamic path planning is using something that came from AlphaGo, which is a combination of partially observable Monte Carlo processing with Monte Carlo tree search. So it's an exploration, exploitation, reward system using information gain. Okay, so the particular metric that we use is KLD, which is Kullback-Leibler divergence, and it is looking at the change relative to the position estimate of the map. As you're going along and you visited something, you have less uncertainty than an area where you have greater uncertainty about the area. Okay? And I'll leave it right there. The point that I'd like to make that's fundamental to this approach that the student was really emphasizing is the notion of self-assessment. And so self-assessment we define as the ability to use knowledge of one's internal state and operating context to understand and predict one's ability to perform a task. So as military planners and as military operators, you can think of 3 phases for self-assessment. One's pre-mission, one's during mission, and one is for post-mission. And so in the pre-mission phase, what you can do is that you can get an expectation as to what the performance of the algorithm is based upon various levels of information within the train. But you have to quantify what the value is associated with that. We have a whole technique to be able to try and do that. This is the way that you train, is that you initialize a scenario with a set of parameters. You have a simulator. This one is known as MAST, which is a higher level than a virtual environment, but could equally as be a virtual environment. And then you have this architecture, which has these components, which is what ATAN is consisting of. You run it, and then you get an idea as to, over time, what was the ability of the vehicle to navigate accurately and produce a map. And you can run that a lot of different times to get a sense as to what the performance of the algorithm would be with assumptions about what the terrain may look like. All right, so wrapping things up, implications for future system architectures. The point that I had made earlier is that there's a dual transformation that is important. And so from a control theory level, is that I think a good way to go is that the classic control methods are retained at the low level. And this is to understand and ensure stability of the system. Give confidence that the system is going to do what we want it to do. But the high-level decision-making leverages probabilistic learning techniques. And they're really advantageous, and we should continue to use those things. But we should also recognize that we need to have insight as to what's actually happening. And what that means is that we need mathematical tools that kind of integrate the two things, the two different approaches. Organically integrate, neural networks with things like Lyapunov stability analysis. And then the final point right there is adopting a federated reinforcement learning framework and offloading the computational load to the web. So that visualization that you saw within the virtual environment is from Amazon Web Services. So all that virtualization happens there. And there's organizations like UUV-RON, Unmanned Underwater Vehicle Squadron, that keeps all their data now on board Amazon, government Amazon web services. What does that allow you to do? That's an enabler, right? You can do all kinds of testing with the vehicles from their data sets in the virtual environments to understand what the success of mission performance might be, for example. All right, so the summary. The OODA loop is quickly being replaced by an embodied AI, and it makes the decision process more opaque and difficult to understand. Really, I used to be a guy that I would always say that simulations are doomed to succeed. And because I was an experimental guy, I always liked getting the robots out in the water. And it's certainly still very important. But the role of simulation has transformed, and it's extremely important with development of robotics because of speed of development, the expenses, and the ability for training and developing of virtual data sets. Self-assessment provides the ability to improve the critical review process in the 3 phases of a mission. And information is, I didn't really talk about this much, but when you look at information metrics, KLD for example, that is all about the probability distribution ratio. But that doesn't tell you about the value of the information. Is that really what you need to do is quantify and qualify and have metrics associated with the information in order to then do better optimization.